Hello, everybody. Thanks for staying here with us. We are almost nearing the end of our AFLOW school. We only have 2 sessions left, and this session here will be about lattice dynamics and phonons and how we can calculate them using AFLOW. Actually, just out of curiosity, can I get a quick yes or no? Who is familiar with phonons? Just in the chat. Some are. See a yes. See a no. Excellent. So mixed bag. Phonons are not trivial. So we can, in these 2 hours, only scratch the surface, but I hope what you can get take away from this is kind of what phonons are and what kind of properties we can calculate with them. Since I'm sure that, since there are some people who don't know much about phonons yet, if you're interested afterwards, I put a couple of books and literature, a little bit of literature into this slide here. The introductory books are very, very nice because they are they use a lot of pictures and a lot of easy descriptions. And the theory of phonons, these books are more advanced, but they are very, very good. I can highly recommend if you are interested to read them. So what are phonons? The easiest description of phonons is that they describe vibrational motions of atoms on a lattice. And these lattice vibrations are a collective property. So we're leaving the realm of unit cells and going to the entire crystal. They are, even though they're fairly complicated, expensive to compute sometimes, they are responsible, or at least important, for many physical properties, like some thermal properties, thermoconductivity, electroconductivity, thermoelectricity, superconductivity, and we can even talk about phase stability using phonons. So let's start with a simple picture to show how atoms can vibrate. Each atom has 3 degrees of freedom, X, Y, and Z. And if we just look at a 1 atom basis, we have essentially 2 ways they can move. They can go perpendicular to the propagation direction, which in this case would be along this axis here, along which these atoms lie, or they can move parallel to the propagation direction. And the former, where they're perpendicular, are called transversal. The other ones are called longitudinal. Here we can see the first 2 atoms are kind of oscillating in a different phase, but the third atom, they move the same way. So it has a periodicity of 2 times A, which is here in this case our lattice parameter. And we can define a Q vector, a propagation vector, which is its reciprocal, which is 2 pi over A times 1/2, 0, 0, 0. These Q vectors are going to be very, very important. If we have 2 atoms, we essentially have 4 ways how they can move. They can all oscillate in phase. Here we have a transversal oscillation where every atom is moving in phase. And the same can be done using longitudinal directions. Here we see they're all nicely in phase and they're moving parallel to the propagation direction. And these are called acoustic phonons because they behave kind of like a sound wave. It's especially obvious when you look at the longitudinal phonon modes. We of course also have the out of phase possibilities, again with transversal and with longitudinal options. And these are called optical phonons because for polar materials like sodium chloride, these phonons can be excited using infrared radiation. This is the transversal optical phonon mode of these 2 atom bases. And here we have a longitudinal one. You see how these atoms essentially move out of phase. When one atom type moves to the one direction, the other atom type moves to the other direction. So these 4 terms you need to really keep in mind: longitudinal, optical, and transversal optical, and the same with longitudinal acoustic and transversal acoustic. Anything with a 1 atom basis cannot have optical phonons because we don't get this out of phase possibility. So how can we calculate how these atoms move? This involves a little bit of algebra here, but I will go through this. If you can't follow along all the steps, that's not that big of a deal, as long as we grasp the general concept. But since we're dealing with the entire crystal, not only with the unit cell, I need to introduce a little bit of notation and terminology here before we can move forward. And the one thing that I would like to Okay, I get the question, what did you say can't have optical phonons because they can't oscillate out of phase? Any crystal that only has one atom in its basis. So for example, a simple primitive cell with only one atom cannot really oscillate out of phase. Yeah, you're welcome. So dealing with the supercell, dealing with an entire crystal kind of forces us to define supercells. When we have, let's look at the shaded cell here. The shaded cell here is our unit cell, and anything else is just a copy of that unit cell. And this entire thing here, this entire construction is called a supercell. And we have two different indices. We have an atomic index that we need to use, and we have a supercell index that we need to use. Anything that's inside the unit cell will have a 0 for a supercell index. And here we have a vector that goes from its origin to an atom in the supercell. And here we have a vector that points from the origin to the origin of that supercell. These will all come up later. Here's another example of a different atom type. And here we have another vector that points to the origin of the supercell. So in order to calculate these equation of motions, we need to figure out how we can describe the crystal. One thing to describe the crystal is its potential energy. This form of the potential energy is just a Taylor expansion, and it's basically just some term here, the first derivative of the potential energy times an atomic displacement. And we can keep this going until infinity, but we're not going to because that would be a ridiculous calculation. But we can make a simplification with this term. In equilibrium, this term here, the first derivative of the potential energy with respect to displacement, which is the negative of the force, is 0, because if there was a force anywhere, it wouldn't be in equilibrium. So that term is gone. And then we make the approximation that we truncate everything after the quadratic term. And this is called the harmonic approximation because it looks kind of like a harmonic oscillator. This term here, we will see quite a lot in the next few slides. It's called the harmonic force constant. It's the second derivative of the potential energy with respect to two different atomic displacements in equilibrium. So the equation of motion is really just simple Newton mechanics. Mass times acceleration is the force. Force is the negative of the derivative. It's the negative of the derivative of the potential energy. And this is a differential equation which has the following solution right here. Here we have a wave term and some displacement of the atom in the unit cell weighted by the square root mass. So now we have to go through a little bit of algebra. When we just plug in that solution into the left-hand side of the equation, we take the second time derivative. We have the square of the frequency, but other than that, it looks fairly unchanged or mostly unchanged. The other term, the right-hand side, is the derivative of the potential energy with respect to the displacement, which leads to that particular form because we can just get rid of that one displacement and we plug this in the solution in here and we get to the form on the very right. Now when we just plug this into the equation of motion, we get to this equation here, which looks pretty hideous and not really something that we want to deal with that easily, but we can make it a little bit simpler. First of all, we can cross out, we can get rid of that negative sign because that cancels out. The next thing we want to do is we want to move all of this over here, the entire term. And that has the nice side effect that the frequency component gets canceled out, so time component gets canceled out. And we end up with the one, with this form on at the bottom here. And we can make a further simplification because this term here does not depend on the index of the supercell, so we can move this one out. And that can be further simplified by just summarizing this sum into this component here. And let's look at these components closely. We have a scalar, omega. Then we have a displacement component here, which is a vector component. So we have a scalar times a vector on the left-hand side. On the right-hand side, we have a component with two Cartesian components, which looks like a matrix, and it is a matrix. And we have something here that is, again, a vector. So a scalar times a vector equals a matrix times a vector. And that is a fairly simple eigenvalue problem here. So frequency squared times an eigenvector equals a matrix times an eigenvector. This index lambda here is a kind of a combined index of our wave vector that we plug in and a so-called branch index. The biggest part that we need to worry about is the dynamical matrix, because if we know the dynamical matrix, we can solve that eigenvalue problem. I actually already gave the name away. This is called the dynamical matrix. And whenever you deal with phonons, you read about dynamical matrices all the time. It comes up constantly. The atomic displacements then become the same solution that we had before, but here we have the eigenvector as the determining factor of our displacement. So if we solve this problem, we can get the atomic displacements, or basically the way the atoms move based or time resolved and with every single atom in our crystal. So to recap, what I would like you to take away from this is that we use the harmonic approximation, which means that we are cutting off the potential energy after the quadratic term. And we have an equation of motion, which is based on the second law of Newton mechanics, which is mass times acceleration is the force. And with a little bit of algebra, this becomes an eigenvalue problem that is actually fairly simple if we know the dynamical matrix, which is shown here below. So now the big question, of course, is how do we get the dynamical matrix? And with this, we need to look at what we actually have in there and what we know and what we don't know. We know these vectors here because we know what the structure is. Q is an input parameter, is the wave vector. And we also know what these masses are because we know what our structure is. What we don't know are these force constants. So now, how can we calculate those? When we look at the definition of the force constant, which I've given a few slides back, I'm putting it back in here. This is the second derivative of our potential energy with respect to two atomic displacements. And we can calculate this using the central difference method, here. And when we do this for the harmonic force constants, we get essentially two terms here. The first derivative of the potential energy with respect to an atomic displacement, while another atom is displaced by this vector delta U. And if we remember that the derivative of the potential energy with respect to a displacement is the negative of the force, we can plug this in and get these two terms, this equation below, where we express the force constants basically just as forces and a displacement. We know what the displacement is because we apply it, and the forces can be calculated using density functional theory quite easily. So the strategy for calculating force constant is going to be, first of all, we need to relax our unit cell structure, and the forces of our unit cell must be as close to zero as possible. Why? Because if we want to measure forces in a supercell later and we have residual forces anywhere, we're just adding noise, we're contaminating our measurement. We're basically just having forces in there that don't belong to the displacement itself. Then we create a supercell structure with displaced atoms. Because of this form here, we need to displace an atom, this delta U here. We calculate the forces using density functional theory. Then from the forces, we determine the force constant, calculate the dynamical matrix, and solve the eigenvalue problem. AFLOW can do all of these things in one single code using APL, the automatic phonon library, which makes it fairly unique. Most codes just essentially do number 2, and they do number 4 and 5, but they don't do everything in one sitting, or at least with one particular workflow. Now, we can't displace every single atom because if we have a huge supercell, that wouldn't be computationally feasible. We can make simplifications. One thing we can use is the translational invariance, which means that when we distort an atom in the unit cell, we don't have to distort the atom in the periodic images either, because it looks the same in each single cell of the supercell. Another thing we can do is we can use symmetry to reduce the number of distortions we need to use. if I displace an atom along the x direction and displacing it along the z direction looks exactly the same, I don't need to calculate the z direction. I can just project x onto z. And that is something where we use the symmetry packages that we have that David talked about quite a lot. The other thing that we need to keep in mind is we cannot calculate an entire crystal because we cannot use 10 to the 23 atoms. That's computationally just ridiculous to use. But the question how large a supercell is something that I cannot answer because it's different for every system. It must be large enough to capture all interactions, and the atoms should not interact with their periodic images. That is like the general guideline I can give you. But other than that, you just have to increase your supercell size until everything converges. That's an unfortunate reality when it comes to phonons. So, talked a lot now. Are there any questions for now? Because we're going to move over now to actually doing this inside AFLOW. This was, I know this was a little dense, especially if you're fairly new, but if you have any questions, just let me know right now before I move on. Nope, I don't see any questions. Then let's move on to how we can do this using AFLOW. So we're going to start the workflow by calculating aluminum. And we start with a simple AFLOW proto command. And adding to that, we also use module equals APL. Dash module equals APL. So it's not just a simple AFLOW proto command, but we add the module APL to that. Oh, of course you need to load the AFLOW module first. It's a good reminder. And here we see the same output that we have for all the other AFLOW proto data, but this is a little bit, the AFLOW in file is a little bit different. If you actually use the dash module equals APL, you see that this line here is not commented out anymore. So it's already starting an APL calculation. And I will go over this later while the calculations are running. There's just three things I would like to change just to make the calculation simpler and faster. So we changed the number of the min atoms to 100, and I'll explain later what that means. We'll change KPPRA to 1000. Polar we changed to off, and we know that aluminum has no magnetic moment, so we can change spin to off. It's all in the slides what you're supposed to do. So then in order to run this, we do AFLOW-run, and then we specify the directory afterwards, which is the directory we are currently in. So it's doing a bunch of symmetry calculations, symmetry output, and then what it does, where is it? Here, it's executing VATS. So it's doing step one of the strategy that I mentioned before. It relaxes the unit cell structure with forces to be as close to 0 as possible. While I do that, I'll go over the AFLOW in file that we have. So there are a bunch of options. The important ones that I would like to mention is this here, DMAC. This is the displacement distance that we're using, and it needs to be fairly small. Because we want to stay in the so-called harmonic regime. If we displace it too far, we're not going to have a linear relationship between the displacement and the forces. 0.015 is a pretty good number. Some others use 0.01, but this is something that you need to test. This is typically a fairly good thing to have. The KPPRA value here, 1000, is actually very low. I'm doing this to make the calculations faster, but this is the K-point density that you're going to use for your supercell calculations. For metals, 3,000 is the absolute minimum. Never go below that. I'm really just using it here to make our calculations go faster. Min atoms is determining how large your supercell is going to be. It is trying to increase the supercell size and then once it has more than 100 atoms, it stops. In this case, we have a 5 by 5 by 5 supercell. If you don't want to relax the structure ahead of time, you can just set relax equals off. And relax commensurate is something that was implemented fairly recently. It scales it makes sure that you have the same K-point density for the relaxation and for your supercell calculation. Zero state on is an interesting feature. It basically calculates the supercell without displacements. It's technically not necessary, but it is very good for troubleshooting if you want to see what your residual forces look like. Is a useful calculation for diagnostic purposes. We can also enable several phonon properties. The phonon dispersion, which is essentially a band structure, is governed by this DC dispersion calculation. We can get densities of states using DOS equals on. We also can get thermodynamic properties, and this here's the temperature regime. We can all get this. Yes, so min atoms is the parameter test to know which supercell size is needed for the results to converge. Is a question. Yes, this is a parameter test. There are some more options you can use. You can also directly specify the supercell. There is an APL README where you can read a lot more about this. I will do, this is AFLOW README equals APL, where you can also specify a supercell parameter. APL supercell is, for example, a 3 by 3 by 3. Then you can really change whatever you want. But I personally recommend min atoms because then AFLOW is trying to increase the dimension at the smallest. It basically tries to keep the volume at a minimum, so you don't end up with a huge supercell in one direction, even though you don't need it. It minimizes the number of atoms, essentially. It's a good question. Any more questions before I move on? Because it looks like VASP is already done. Okay, so VASP has done its calculations. And actually, when we look at the content of this directory, we see it does the relaxation twice for the same reasons that Corey and David explained on day one. And we see we have 3 directories. One is this A0D0P, A0D0M. P is for plus, M is for minus, and the zero state calculation is just an undistorted calculation. So let's look at one specific file, and that is the AFLOW.APL FCCalc state. I want to display it. I don't want to run it. This one is basically explaining a little bit more about what you have in your calculation. What I want you to look at is the distortions tag. This one gives you the atomic displacements. This is atom 0, which is aluminum. And this here is the distortion vector. So we can see it is using a face diagonal as the distortion vector. And these are the 2 directories. So later on, when you want to look at a distortion vector, this is the one to look at. Okay, so we got all our directories, and now all you need to do is you need to run the DFT calculations inside these directories here. They all have AFLOW in files. I can just open one of them real quick so you can see that this is actually a supercell. There's a lot of information here, but this is the structure. You see the description here gives you some information about what the supercell is. It's a 5 by 5 by 5 supercell. It has 125 atoms, and the lower form would be, the other one would be, or the one lower would be a 4 by 4 by 4. Since it's cubic, it always expands uniformly. and you would get 64 atoms. So that's not enough. It went up to 5 by 5 by 5. It's a little bit bigger than 100, so it takes that cell. Here you see we have a displacement of one atom, and the other ones have very nice and round numbers, so these are undistorted. And this is 125 atom supercell, which is a huge cell. I think the calculations we've done so far were iron, silicon here, and those are just one atom. These cells can get really, really big. Some cells, for example, if you want to get good thermal conductivity for boron arsenide, you need a 250 something atom supercell. So this can get fairly expensive. But yeah, as soon as you activate APL, you can just run and AFLOW will relax the structure for you and create all the directories. Are there any questions about that for now? Just preparing, this is one thing, but actually getting properties is another, and I will show you that next before we get into the exercises. Nope, no questions. It's good. So if you look in your exercise directory, we will go over one together. If you go into your exercise directory, you have total of 5 directories. Let's go into the alumina one, because these are DFT calculations that are already finished. It's fairly barren. I just reduced it to the files that we need. And this file here, the QM-VAS file, contains all the forces. I can take a quick peek in here, and we see, oh, this Vim version doesn't like compressed files, I guess. So here, this is basically what VASP outputs. This is the position of the atom, and these are the forces. And these will be processed later to calculate the force constant. So let us go ahead and do that. Let's recompress that file. So in order to run a post-processing run, all we need is to run AFLOW again. And this time it will not relax the structure because it has a pH postcar file in the directory, so it knows it already ran an APL calculation. And here you see it reads the forces from the different directories for plus and for minus. And now it's calculating the symmetry basis. This is the part on APL that takes quite a long time because our symmetry package is very accurate, but also a little slower than some other codes, but I will take slow over wrong. So you saw with David's talk earlier that we do better in a lot of systems. So this is a pain you have to go through once, and once the force constants are calculated, you can just run post-processing with different parameters, and you don't have to calculate it again because it's stored in a file. Okay, now it's calculating the force constant matrices, and it goes through a bunch of post-processing. Okay. So now what we can do is we can actually look at some of the phonon properties. When we look at the content of this directory, there are a bunch of files. There are, for example, atomic displacements in here. There are thermodynamic properties, and there are phonon dispersions and phonon DOS in 2 formats, 1 custom format and 2 also in VASP format. So if you already have a VASP post-processing tool for band structures and densities of states, you can just use the same tools for phonons. So let's plot one of these phonon densities of states and phonon dispersions and get a combined plot. Basically just what we did with the band structures. The commands are very similar. And we do this with that file name, ph phonon dispersion. DOS is the keyword to plot dispersions, densities of states. This one is just the name of our output file. My slides say -- print equals PNG. If you don't add that, you get a PDF instead. And did I make a, oh, need to add plot to that. So plot ph disp DOS, just like you have it on the slides. That happens when you plot the first time. It's using PDF LaTeX. It's just setting the font. You only see this message once. So don't be alarmed when you see that. And here it is. I also have it on the slide. So when we look at this file a little bit more, we see we have, especially looking here at this path between W and K, we have 3 different branches. In Phonons, they're called branches. The band structure, they're called bands. And that is exactly what we want to see. We only have 1 atom and we have 3 degrees of freedom. So we should see 3 branches. If you have 2 atoms in your cell, you will see 6 and so on. So it's good that we don't have more than those. And we see here a fairly linear relationship between gamma or near gamma. And that is something that we want to see. If you look at the literature provided to you, you'll see why. But there's essentially 2 transversal acoustic branches and 1 longitudinal acoustic branch. We don't see an optical branch because aluminum only has one atom. We also have a density of states here, and that density of states can be used to calculate, or is used to calculate, thermodynamic properties. And you can actually plot all these thermodynamic properties using plot thermal. See, you don't get any LaTeX messages anymore when you do that, and you suddenly have 4 files in here. You get files for the heat capacity, the vibrational entropy, the vibrational free energy, and the vibrational internal energy. And all these can also be viewed in the file thermodynamic properties.out. See, where is it? Here. Here we have a couple columns. This is the 0-point energy. This is the internal energy, the vibrational free energy, vibrational entropy, and the isochoral heat capacity. So this is a very important property because sometimes your reactions depend on the vibrational components. So if you calculate, you can calculate a reaction vibrational free energy difference. And sometimes systems that have a positive reaction enthalpy, so at least in chemistry, it means that the reactants are more stable, but the reaction still takes place because of the vibrational contribution. So this is an important property to look at. Another file I would like to point out that is very interesting are the displacements. They depend on the temperature, and I already showed that we need the eigenvectors for this. These are the mean square displacement. As we can see, they're very small. They're very, very small. They're just 0.003 square angstroms. So these displacements are not big. The vibrations are not big, but they do determine the properties that we see. So just to recap, went through this. Here's the phonon dispersion. If you didn't get to make your own, here they are on the slide. These are the formulas that we're using to calculate the properties. I just put them on there for your own edification. The Maradudin book derives them very well, but I don't expect you to remember any of these formulas. And here are the plots. So the internal energy rises with temperature, the vibrational internal energy, whereas the free energy goes down with temperature. The entropy has kind of an interesting like S shape and goes up at some point quasi-linearly with high temperatures. And the heat capacity kind of plateaus at 3 Boltzmann constants. Just a quick hint on APL, they're currently all output per cell, not per atom. So you need to divide it by the number of atoms. Another thing that I wanted to mention before I plunge into the exercises, phonons or bosons. They follow the Bose-Einstein distribution. And when we look at the formula, low frequencies have a much higher occupation number at low temperatures. So low temperatures, you mostly have low frequency contributions, and at higher temperatures, the higher frequency come in more and more. And with that, I would like to you all to do your own exercise. This is all going to be post-processing. You will essentially do the same thing that I've done with thermodynamic properties and the displacements. So unless there are any more questions, why don't we all go into our breakout rooms? And let's say 20, 25 minutes. And if you, for the exercises, does that sound good? It does. Let's go into the breakout rooms, and I will see you back here in 20, 25 minutes. Yeah, let's discuss the exercises. You all had a few systems to look at. First of all, which displacements were created. When you look at the fccalc state file, you'll see that for the magnesium oxide, the cubic structures, this is all essentially the same face diagonal displacement vector, which is very common for all these cubic structures. Zinc sulfide is hexagonal, and that vector looks a little bit weird, but it is actually a body diagonal vector. That's kind of the whole Cartesian versus fractional coordinate representation. So the average mean square displacements, you probably notice that the atom with a higher mass has a smaller displacement. That actually makes sense when you think about it, because the lighter an atom is, the more it can actually move. And we see this consistently throughout. For example, boron and arsenide. Boron is much lighter than arsenic. Zinc is much heavier than sulfur, and so forth. Oh wait, is it the other way? Yeah, zinc is heavier than sulfur. Zinc is lighter than sulfur. Anyway. Yeah, we see a good scaling with the mass. The heat capacity, since it's all printed by cell, can have widely different values. For zinc sulfide, it looks very large, but when you actually break it down per atom, they're all somewhere between 2 and 3 kBs per atom. The densities of states, the projected ones, so that's why we added that term at the beginning. The projected densities of states can be calculated with that, with the DOS project equals on. I didn't do it for aluminum because it's a little silly to get projected density of states for only one atom. But let's compare them a little bit. So we see with magnesium and oxygen, we have magnesium mostly at the lower frequencies, but oxygen is also very much in there. And that's because these masses are very, very close together. So you have a lot of overlap in the contributions, whereas for boron arsenide, you have arsenic basically completely at the bottom and boron completely at the top. Higher masses are lower frequencies because the dynamical matrix is scaled by the inverse of the square root of the masses. So higher mass, lower frequency. You see this throughout niobium carbide, you see niobium down here and carbon up here. And zinc sulfide, you have a little bit more of an overlap. You have zinc, which is heavier at the bottom, and sulfur mostly at the top. So you can actually kind of engineer your phonon gap, if you will, by just having like atoms with different masses, which is very important for thermal conductivity, for example. This is one way how people try to look at or engineer new high thermal conductivity materials by having different masses and also covalent bonds, because then you have different force constants that are more favorable to thermal conductivity materials. So I promised that I was going to talk about what polar on and off means. And for that, we need to actually take a look at what happens when we have a polar material. So let's look at the optical phonon modes. It doesn't happen with acoustic phonons. With optical modes, this happens. We have two atoms here. Let's say this blue one here has one charge and the orange one here has another charge. And they're moving towards each other because they're trying to oscillate. In optical phonons, they're all out of phase. So here it is after movement, and they're trying to return to their equilibrium position by moving away from each other. However, if they have separate charges, these two have an electrostatic attraction. So there's an additional force besides the one that drives them back into the equilibrium position. When we look at the transversal optical mode, here they're moving apart, but this time from the top to the bottom to the top. When they move back, the forces that attract these oppositely charged atoms to each other point into the same way that they're already moving. So you have a different set of forces acting on each other. So the longitudinal optical modes and the transversal optical modes get split at long wavelengths. So the LO modes add additional restoring forces, longitudinal optical ones. And they have a higher frequency. And literature constantly talks about this as LOTO splitting. And we see that in polar materials. So that's why we didn't need it for aluminum, because aluminum is not a polar material because there's no atoms with different charges. It's only aluminum. So for any kind of elements, you don't need that. You don't need to worry about this. And you don't need to worry about this for metals either, because you don't have that polarization in your material. The splitting only occurs at long wavelengths because or small q, because the Coulomb interactions are very long range. And the splitting occurs near the gamma point, but not directly at the gamma point. However, standard potential energy approximations like the one that we used does not take that additional force into account. It only looks at the simple equation of motion of the atoms. And there is a non-analytical term correction, that's the name of it, that must be added to the dynamical matrix additionally near the gamma point. And this is the formula. I'm not going to derive it, and I'm not going to explain it too much. I just want you to look at two things. The one thing I want you to look at is this Born effective charge tensor, these two. So the higher the charges are, the more the correction takes effect. The other thing that you need to look at is the dielectric tensor. And the higher the dielectric tensor is, the less is the correction, or the other way around. The smaller it is, the larger is your correction. So materials with large charges and small dielectric tensor values have a stronger correction that is necessary than lowly charged and with a higher dielectric tensor. And there are multiple mechanisms or multiple formulas on how to apply this. We use the so-called Wang formula, and let's check it out a little bit. We are going to, maybe for 10 minutes, back into the breakout rooms. And I want you to look at this file here, the APL polar.xml, and just take a note of the Born effective charges in the dielectric tensor. Then I want you to just open the AFLOW-in file and set polar in these to off. In the AFLOW-in files to off, and just run AFLOW again. Should be fairly quick. Either rename the log file or use the use log feature to use a different log file name, otherwise it won't run. And then just plot the phonon dispersions and see if you see a difference. It kind of depends on which system you have. So let's go back into our breakout rooms. So let's go a little quickly through the different compounds. So magnesium oxide is a very, very ionic and very polar compound. So as you can see, there's a huge difference between nonpolar and polar corrections. At the gamma point, or near the gamma point, I should say, the difference is pretty tremendous. So you get wrong phonon dispersions if you don't include these corrections for magnesium oxide. And you can see we have large charges in a small dielectric tensor. Boron arsenide, there is a difference, but it's barely perceptible. It is a semiconductor. It's not a metal, but it does have very small Born effective charges, so we don't see much of a difference. Zinc sulfide is a very interesting case because it's not cubic. You see a difference when you look at the gamma point here and compare this. We see a difference in the frequencies, but also look at how different it is when you come from the K point to the gamma point and when you come from the A point to the gamma point. They're not the same frequency near the gamma point. So the correction depends on the direction that you're coming from in Q space. For non-cubic structures, that is the case. For cubic structures, it's not the case because of symmetry. And iron carbide is a metal. Look at the huge dielectric tensor. There is no difference between the two. So generally, if you have a metal and if you have elements, you don't need to use the polar correction. Other than that, you need to use the polar correction. And you need FAST5 for it. FAST4, unfortunately, cannot calculate them, which is why we had to turn it off for aluminum. So that's all nice. We can get some properties, we can get phonon dispersions, but we're talking about atomic motions. I don't know about you, but staring at a band structure doesn't really help me visualize how that actually looks like. And this is what we're going to talk about for most of the remainder of the time. So let's recall the atomic displacement vector. It is some kind of amplitude times a phase factor that oscillates in time and space, and an eigenvector. And let's look at magnesium oxide in the X point. The X point is half-half zero or some other symmetry equivalent variety, but we're looking at half-half zero. And when we just plug this into the vectors for reciprocal space, we get to a Q vector of 2 pi over A times Z. So this particular point propagates into the Z direction. And we can visualize this by here, this way. This is how this particular phonon mode looks like. This is the longitudinal acoustic phonon. We can see it as acoustic when you look at, let me mark this with a pen. When you look at this atom here and this atom, they're in the same plane and they are oscillating in a similar way. And the periodicity is exactly one lattice parameter. Here's the transversal acoustic mode. We see this, remember the Z is the propagation direction. It is transversally oscillating in the Z direction. We can also show the optical modes. These are the transversal optical modes. We see that these two atoms, these two red atoms, which are the oxygens, are oscillating out of phase. And we can do the same with the longitudinal optical modes that are also oscillating out of phase, but this time parallel to the propagation direction. And with the help of an external program, we can actually visualize these phonon modes. And I will demonstrate how that is done. This was created using XCRYSTEN with our AFLOW interface. And I will demonstrate how to do this. And for that, I need to go back to the Turbo VNC. I put the instructions on the slide. So I have magnesium oxide ready. And actually, let me ask, is there a question? Do you want to see, is there a phonon mode that you want to look at a little closer that you quite didn't catch? If that's not the case, I will show you how to generate scene files to create a GIF with these visualizations. You can do this actually with any Q point. The only requirement is that you need to have this file here, the harmonic IFCs file. You only need the force constants for this. So the command for that is visualize phonons. And then you need to specify a Q point or multiple Q points. In this case, half-half 0. And the other thing that you need to specify is a supercell. So let me get back to this here. So as I said, the propagation direction is the z direction, and the wavelength for half-half 0 is 2 times a. So you need to have a supercell that's large enough to accommodate all of these to accommodate the oscillation. If you use a, I don't know, a 3 by 3 by 3 supercell, then you have 1.5 periods in there, which is not going to give you the correct oscillation. So the supercell should be inversely proportional to your Cartesian coordinate here, this one. You can always, of course, have a larger supercell. So I could also use a 4 by 4 by 4. They need to be commensurate. That is the important part here. And you can also choose branch indices, but what happens now, yeah, that's what AFLOW is. It's not complaining about it, but it's just telling you didn't select any branches. So we calculated for all the phonon modes that we have. Takes a little bit to calculate the eigenvectors. Okay, so we have 6 files here, 6 branches. Magnesium oxide has 2 atoms in its primitive cell, and we have 3 times as many branches as we have atoms. So now what we need is the program xcrisden. Xcrisden is a code that visualizes atomic. It's actually designed. It was designed to visualize just structure files, just like Vesta or Crystal Maker. But something that it can do, it can import animation files, animated xcrisden structure files. So this is an older version. We didn't manage to get a newer version installed on the platform, but the newest version has very, very nice graphics. This one here is a little older, but it works just as well. So let's look at an optical mode. 1, 2, 3 are always the acoustic modes. 4, 5, 6, and anything higher are optical or other modes. Let's take this one. That's magnesium oxide here. You see the 2 by 2 by 2 supercell, but it's not quite ready yet to get a nice GIF because there are periodic images and we don't necessarily want to see them. So first thing I want to do is I want to get the asymmetric unit. These are the atoms that will be distorted. This is the primitive cell. For the GIF that I've shown here, I calculated on a conventional cell. You cannot quite transform the atoms yet, but I will work on this. It will be in AFLOW in the next 1 or 2 versions. So yeah, we can also display the coordinate system. And let's see, we have the z-axis here. And we can display the forces too. This is the direction in which the atom is going to move. The arrows are very, very long. So what I like to do is change just the force scaling factor here. So this one shows just where that oxygen atom, where this oxygen is about to move. And we see here as well that the magnesium atoms are also moving a little bit, but not quite as much for that mode as the oxygen atoms. This is not a surprise. I picked an optical mode and oxygen is lighter. So we expect oxygen to be more involved with this mode. And another thing that I would recommend you do is go to, sorry, I was a little fast, go to modify atomic radius. And I would set this to 0. to get rid of all the bonds. Bonds are tricky. When they move, at some point they might get out of that radius, and then the bonds just suddenly break in the animation. That just doesn't look very good. On the other hand, trying to find the right balance that it doesn't suddenly have too many bonds is a little tricky. So I like to turn them off, and I find them also just very distracting. So what else? I think that's all for now. So this is just preparing the oscillation. So let's find a good perspective, good zoom level. Okay. So if you close this one, it's not a problem. If you close this one because it was in the way, that's not really a problem. You can also just go to modify, and then you have animation controls. And here's where the actual recording starts. So you see, these are slides. I can kind of move it from one to the place to the other, and that is just one period. But when you expand this menu and you select animated GIFs, and unselect this flag, you can unselect this flag. It's not something that you really need to do. You can edit the conversion parameters, but that's, in my opinion, not something that you actually need to do. And then you can start the recording animation, or start recording the animation, and then you just go through the slide again. This is a little slower because it basically takes a screenshot, a screenshot of every single frame, and then converts it into a GIF as soon as you save it. So this is magnesium oxide, and this would be mode number 4. Right, the standard picture viewer cannot interpret GIFs, so I open it with Firefox. Firefox works. And here we are. Let's see, it's 4:35. Why don't we try this in a breakout room for, let's say, 15 minutes, and then I have some concluding remarks and some other topics, and yeah, we can reconvene in 15 minutes. It looks like most people are back. So if there are no other questions, I don't see anything in the chat, then I will just have a few concluding things to say. I already mentioned at the very, very beginning that we can also look at phase stability with phonons. And something that I've so far just assumed is that we were in equilibrium. But what happens when we're not? So in equilibrium, displacements always increase the potential energy. Otherwise, we wouldn't be in equilibrium. So forces are always restorative, and that also means that our assumption is valid. Forces are restorative, and that also means that our assumption that omega is real is valid. So what happens when we're not in equilibrium? So we have a structure that is unstable. Then we have a displacement that can decrease the potential energy, and the forces are not restorative. In that case, we have a switch in signs, and this leads to an omega square that is smaller than 0, which means that we have imaginary frequencies. And here's an example of how that looks like. Many plotters, and ours is not an exception here, display imaginary frequencies as negative frequencies, but they're not negative, they're imaginary. So anything that's below 0, it has an I in front of it. Beta titanium is BCC. It is unstable at room temperature. And above 1155 Kelvin, it can occur, and it does occur. And when we look at the phonon dispersions, we can see why it doesn't appear at low temperatures. This is hexagonal titanium. It has all positive, all real frequencies, but beta titanium, BCC titanium, you see has huge imaginary frequencies at the end point and at the P point, here again, P and N. And that means that it is not stable at low temperatures. So these imaginary frequencies can also be artifacts. So you really need to be sure that your supercell is large enough, that your K-point density is large enough, that you actually have accurate forces. But when you're sure of that, then you have an unstable structure. And when we look at the minima, for example, here at the endpoint and at the P point, we can even see what the supercell of that displacement is like. So this endpoint of the BCC structure is 0, 0, 1/2, and that corresponds to a 1 by 1 by 2 supercell. It's always the inverse. P is a quarter, 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 and that corresponds to a 4 by 4 by 4 supercell. So at high temperatures, these displacements are large enough that the BCC structure gets stabilized, but it only happens at very, very high temperatures. And phonon calculations, just like any DFT calculations, are at 0 Kelvin. What else can we do? We can expand the harmonic approximation. AFLOW has both of the expansions. The quasi-harmonic approximation is essentially phonon calculations at different volumes. And that can be used to calculate thermal expansion and other mechanical properties like the bulk modulus. But this is something that we cannot discuss today because we already, we don't have enough time for that. The other thing is including higher order contributions. We truncated our term after the quadratic contribution, but we can go higher. We can do the cubic terms, the quartic terms, any terms essentially in the Taylor expansion. And this is the what AAPL does, the anharmonic automatic phonon library. We can include third order contributions, and these include phonon-phonon interactions, which you can use to calculate thermal conductivity. It is very expensive computationally. For example, boron arsenide with a certain cutoff radius of 6 shells requires 144 calculations to get all the interactions. So very expensive. And even the post-processing is very expensive. It's an incredibly computationally extensive calculation. But here's a plot for diamond and thermal conductivity here. It's a very high thermal conductivity material. But since it's so expensive, we cannot really demonstrate this here. Another thing that AFLOW currently cannot do, but might be in the future, can use so-called renormalization effects, where you include temperature effects on your phonon, frequencies, and that leads to self-consistent phonons. And with that, I don't have anything else to present. If you have any more questions, feel free to post them in the chat. And other than that, let's take a 5-minute break or so, and then we have our last talk. Cormac is going to talk about machine learning in AFLOW.